Yeah, just to sort of show that, the state of the art in ISM is actually quite. ISM is a mess, by the way. It's not like stars that, given the mass of the star, its luminosity, you measure the flux using the telescope and you get its distance and so on. You can have any ISM cloud of any size. It can be at any distance from you. There are no like, general uh, principles. So it's a little harder the ISM. Generally, the dark matter is the easiest. As long as you are just concerned about gravitational interactions. Stars are also sort of more or less the same because they only interact gravitationally. But interstellar medium, you have gas. The gas gets shocked. The gas gets excited by collisions. De-excited by radiation. Gas can be excited by background radiation and whatnot. There can be magnetic fields, cosmic rays. It is really like a complex, very complex system, right? But it's also very, very important. So it's sort of, you know, and especially if you go to higher density, uh, cooler phases of the ISM, it almost has the same complexity as the question of how did life originate on the Earth. There is a lot of complicated chemistry, uh, the grains, dust grains mediating that chemistry and all that. It's an extremely complex system. Okay, so you have to keep this in mind, uh, and it's extremely dynamic. Of course, you have dense cold regions which form stars, and then you have supernovae explosions which destroys gas, which is the fuel for star formation. So that, you have things going either way. Forming stars, you know, gas being blown away, all these things happen dynamically. So there are no like beautiful theories in the ISM. It's the real, it's an extremely messy place to apply physics. So there are a lot of like heuristics which may end which may turn out to be almost entirely wrong also. So there is also a lot of scope for discovery. If something is complicated, there's a lot that we don't understand. There's a room for a lot of new discovery. Okay, so these were the books. So this is ISM overview. I mean, this is the disk of the Milky Way. There are stars which are shown here. And this hatched stuff here shows the ISM. So a lot of stars are in the disk. They have mostly circular motion around the center of the Milky Way. So just like our sun, right? It has a 220, or about around about that circular velocity, but it also has of order 10 kilometer per second random velocity. Not just the sun, but younger the stars, the thinner their distribution is, the lower their random velocities are. Uh, the random velocities um, determine the scale height of the stellar distribution. So yeah, so there is this interstellar medium disk. Interstellar medium is not like, does not have a uniform distribution in temperature. Like it's not like you have equal mass across all the temperatures. It's extremely complex too. So there are so-called phases of the ISM. So there is a tendency for the interstellar medium gas to occur preferentially at certain temperatures. And that is to do with physical processes like radiative cooling, atomic, basically atomic physics, and interaction of gas with radiation determines where the gas in the ISM likes to sit. Okay. Now, yeah. So what about mass budget? Like what fraction of mass is where, and what is the mass flow from one part of stellar ISM system to the other? For example, you have this interstellar medium, this gaseous interstellar medium here. It is fed by infall of gas from the intergalactic medium. So you have a galactic disk, ISM of about 20 kiloparsecs total. Now it's surrounded by a huge reservoir of gas known as the circumgalactic medium. And this circumgalactic medium is connected to the rest of uh, the universe through these filaments, which we have actually seen. And the galaxies are distributed in sort of filamentary structures, gravitating structures, and these filamentary stuff uh, seem to be coming towards these uh, nodes of these filaments where there is a higher mass concentration. So this stuff, this dark matter which flows along the filaments, also brings in baryons along those. And those baryons eventually make it to the ISM in a very complicated journey, uh, because those can be stripped, can be put in the CGM, circumgalactic medium. Some of that CGM gas can cool and further go in. You have supernovae explosions and AGN activity which throws this gas out. So it's a very complicated inflow outflow system. But on average, you need the ISM to be replenished. If suppose you had the ISM and suppose it was not replenished by fresh gas, if you put in the star formation rate of the Milky Way right now, about a solar mass a year or 1.3 solar mass a year, this is what's to say. So if you take how long will this ISM last if the star formation rate is this? It's just gas mass, ISM gas mass divided by the star formation rate is the time over which the ISM will last if it continues to form stars at this rate. If you plug in the numbers, it's about a few gigayears. So basically, if you don't replenish the interstellar medium over a time scale of a billion years, you will have no ISM. So that means over a cosmological time scale, over the time scale of the lifetime of the galaxy, you need material to come in from the IGM, from beyond the ISM. Gas from the IGM should make all the way to the ISM. I mean, in order to sustain the star formation rate in the it's a good question, but this is an observational fact that the ISM needs to be replenished at roughly this rate. Now, what makes it flow is a good question. You can have the CGM is more or less hydrostatic, but you can have clouds condense out of the CGM, and the clouds, which are denser than their surroundings, can actually fall, right? They are heavier than their surroundings and can fall and bring in mass. You can have IGM filaments that can penetrate the CGM and bring in mass. You can have supernovae happening in the disk of the Milky Way, and they blow out a lot of energy, but all this hot gas can actually return back in some sort of a fountain flow, except that it can actually bring in gas from the diffuse halo on its way back. So there are a lot of processes which can actually bring in gas to the ISM. At all times, yes. Why should it? Right, the atmosphere is dense at the bottom compared to on Mount Everest. Right, so it's not just following. There is gravity. Right. Okay. Okay. So these are they are very similar, except that you sort of roughly define CGM, IGM, and ISM the following way. ISM is this disk thing. ISM has, on large scales, it is supported by angular momentum. CGM is more diffuse. It sort of is spread out over scales of 100 kiloparsec, whereas ISM is 10 kiloparsec. And IGM is like everything beyond the halo of a galaxy. So this is roughly the division, but they're not like very precisely delineated from each other. Okay. So this is the ISM. ISM mass is about 10% of the total stellar mass of the disk. So it is a small mass compared to the stellar mass in the Milky Way. As I mentioned, the star formation rate is about 1 solar mass a year. Star formation rate in the Milky Way is about a solar mass a year. Do you remember how we measure the star formation rates? Very, very briefly, we went over these different diagnostics. There are infrared diagnostics, UV diagnostics, radio diagnostics, which are proportional to the star formation rate. So there are like various ways of measuring the present, the instantaneous star formation rate using these observational diagnostics. Okay, so this is the mass that goes from ISM to stars through star formation. But stars also die in form of supernovae and black holes, forming and also forming white dwarfs, right? In that process, they also lose a lot of their mass, especially metals, to the ISM, right? So this is that arrow. You recall this model that we did last time of the metallicity, that there is this return fraction and there is something called this yield from star formation process, which produces metallicity back into the ISM. So this is basically related to that. This is the return of gas, especially metals, right? Metals are all cooked inside stars and are thrown out in massive stellar winds and in supernovae. So this represents that. Okay, and out of these, and a small. Okay, so novae are explosions on the surfaces of white dwarfs. They are not catastrophic events, right? So you can have, and they are related to surface nuclear burning. So a white dwarf accretes matter from its companion, and accretion can raise its temperature, and if you gather enough mass, it can burn explosively. So it produces, the star brightens. Nova means new star. So a nova is about a factor of 100 dimmer than a supernova, and they're older. So type 1a supernova, on the other hand, is the cataclysmic death of a white dwarf, right? There is nothing left after type 1a supernova because everything is burned in the nuclear fusion detonation, which sort of all the white dwarf matter is burned. But in this nova, only like small fraction of the mass on the surfaces is burned, and you again have the white dwarf remaining. And a small fraction goes into remnants of stars like these. So finding distances to ISM clouds, for example, is actually quite hard, unlike distances to stars. Because for stars, once you know the mass, it's how its spectrum would be, and everything. So how do you find the distances, distance to clouds? For example, H1 clouds, neutral hydrogen clouds. If you recall, we had this, we did this rotation curve stuff at the very beginning, that if you have a 21 centimeter emitting cloud, you can actually measure the line of sight velocity or the radial velocity. And if you assume circular orbits, the radial velocity is just V naught, R naught sine L times omega R minus omega naught, right? So there is a 1-to-1 mapping between this Doppler shifted line of sight velocity and the distance of the cloud from the galactic center. So from that, we can actually measure the distance of the H1 cloud. So that is a kinematic distance, assuming that the gas is going in circular orbits, but that is not always reliable. Okay, good. How else can we measure the distances to ISM clouds? So we can measure the distances to stars, and by looking at the absorption features in the spectra of stars, we can actually suppose you have two stars, okay, at different distances, and they're almost in the same part of the sky. If you measure the spectrum of the closer stars, so for measuring distances to stars is easier, right? Because you know what type of star it is, uh, then you know what its luminosity should be. So measure the flux and know the distance. So if you have these two stars, look at the absorption features in the two stars. Right? The ISM absorption features are narrower than the stellar absorption features because stellar temperature is thousands of Kelvin, whereas the ISM absorption is a lot of times dominated by much cooler gas, like 100 Kelvin, 10 Kelvin, something like that. So you have thinner features, and the the extra absorption that the background star has compared to the foreground star just gives us a sense of what's present between those. So these are the kind of things that people use to measure the distances to ISM clouds. Okay, not as clean, but you have to live with what you have. Okay, so right, so this is how mass distribution in various phases of hydrogen, right? Hydrogen is the most abundant element. So H2 means proton, essentially, fully ionized hydrogen atom. This is protons. H1 is neutral hydrogen. H small 2, or uh, this Arabic 2, H2 is molecular uh, hydrogen. So total H2, not including helium. So this is just, so these are roughly the masses, uh, and most mass is actually in the neutral medium, so about 60%. Again, these are like very rough, so don't take them very seriously. But these are like indicative. Uh, this is molecular gas, and this is ionized gas. Okay. So mass-wise, the neutral H1 is the dominant component of the ISM. Okay. Now, these are some of the tables from the book. Actually, these are some of the properties of these different phases. I mentioned that the ISM likes to exist in certain temperature ranges. Okay, so we'll actually slowly go through this table. So the hottest phase is the so-called coronal phase, or the hot interstellar medium. Okay, like about 10 to the 6 Kelvin, very hot actually. Uh, and the hottest phase is also the least dense. These phases are roughly in pressure equilibrium with each other. So if some phase is hot, its density is lower because N times T, which is the thermal pressure, is roughly equal across different phases. FV here is the volume filling factor. That is, what is the fraction of volume in the ISM occupied by this hot interstellar medium? It's about 0.5. So a hot gas occupies a lot of volume. Okay, even though it occupies a lot of volume, it can actually have a smaller fraction of the mass because its density is low. Okay. So these are some of the typical numbers. This is sort of the mean density. So this is the density of the hot gas itself. Now, particle density in the hot phase. This is average density. So you multiply by FV because the volume occupied by small. So you take the total number density or total number of H2, which is very hot, divided by the total ISM volume. This is this guy. Okay. Average rate of supernovae in the Milky Way at present is roughly, uh, 2 per 100 years. On average, there will be 2 supernovae in the Milky Way over 100 years. I mean, this is just an average thing, you know. Milky Way hasn't had a supernova in last 300 years since, you know, humans started observing intensely. But that's, you know, that's just by chance. There were actually a lot of supernovae before. The Tycho supernova, there is Kepler supernova, these guys, and Tycho and Kepler were not that far apart in history. So there has been more time since then, and no supernovae happened in the Milky Way. Okay, let's see. They are collisionally ionized. Since it's hot, you know, collisions can knock off electrons from a neutral hydrogen. They're either expanding or in pressure equilibrium, cooling by adiabatic expansion. Hot gas at these temperatures, 10 to the 6 Kelvin, emits X-rays and UV. And sometimes it can also produce radiosynchrotron emission. Okay, so this is hot interstellar medium. This is warm interstellar medium, or WIM, not WHIM. That's warm, hot intergalactic medium. I'm not. This is part of the ISM only, the dusky part. This is H2 gas. So this is around 10 to the 4 Kelvin, volume fraction this much, density this much. Okay, so you see, there is a great range in H2 density. Now, I said that this is in hydrostatic equilibrium, but this cannot be if there's such a big range. So some of these densest H2 gas is near stars, okay? And these are self-gravitating regions, like deep inside molecular clouds. And since they're self-gravitating, their pressures are much higher than the general ISM pressure. So that's why these are basically pressures of the H2 regions, these, you know, ionized regions around massive stars. Okay, but this 0.3-ish value is in the diffuse WIM, diffuse warm interstellar medium, which is not self-gravitating, which occupies a lot of volume. You know, so this one is in pressure equilibrium. So right, this times 0.3 is roughly this times 0.004. Okay, so these are heated by photoelectrons from hydrogen helium. These are photoionized, like UV radiation from stars and from the ambient universe can ionize neutral hydrogen and helium, and, you know, produce this ionized phase. So this phase is photoionized. This is how the gas at this temperature is maintained ionized, by strong exposure to UV radiation from stars. Here, the ionization happens because of shocks. This is collisional ionization. Okay, cool. These are different cooling processes. So there are heating processes and cooling processes, and in equilibrium they sort of balance, and that's why you have these long-lived phases in, you know, on long time scales. So you have optical line emission, for example, H-alpha emission, Lyman alpha emission. All these will take away energy from these free emission. Fine structure line emission, like a C2, carbon 2, singly ionized carbon, emits at 158 microns. It's one of the important coolants of, actually, yeah, I'm not sure about if it is for this one or for this. I think it's for the cool CNM. In CNM, hydrogen is neutral, but carbon can be singly ionized. So I think that was here. Fine structure line, the C2 is here, actually, not here. But there are other fine structure transitions at this temperature. Warm neutral medium at 5,000 Kelvin. You know, they are more or less about the same. I don't think you need to even distinguish between these, because no, you do, because this is ionized and this is neutral. At about the same temperature, this is neutral. So this gas will produce 21 centimeter emission and absorption. This will not. Right? This is not a neutral hydrogen. Okay, but the conditions are very similar. This is cold neutral medium, C and M, at about 100 Kelvin. And N times T is roughly constant. These are also heated by photoelectric heating from dust. Have dust particles, and you have UV photon or starlight kicking it out, and that released electron has extra kinetic energy that it shares with these neutral phases. So all these heating cooling processes are very, very important to determine the rough density and temperature of the phase that you're talking about. So this 158 micron line is important here. This is cold neutral medium. This also emits and absorbs 21 centimeter. Except that the absorption, cold neutral medium is very efficient at absorbing H1. So most of the time you are sensitive in the absorption, sensitive to the cold gas, but in emission you're sensitive to both this and this. We'll actually do H1 radiative transfer a little bit later. This is diffuse H2, diffuse molecular gas. Just as H2, this ionized hydrogen gas, you can have diffuse H2 and you can have dense H2 in H2 region. Similarly, this molecular gas, you can have diffuse and also dense, the self-gravitating molecular gas. So that's why the density here is huge compared to that. Anyway, you guys can actually check it out. Cooling of this happens through dust emission, and it also emits the CO emission. Carbon monoxide molecule is about 10 to the minus 4 times abundant than molecular hydrogen. But molecular hydrogen is not a very efficient radiator. It does not emit energy very efficiently. It has, it has rotational transitions, but those are not easily, they are sort of forbidden transitions. They are not easily excited because H2, molecular hydrogen, has no permanent dipole moment, whereas CO has a permanent dipole moment and it sort of increases. There are these dipole transitions which are allowed. So CO emission, line emission, is the tracer of CNM. Molecular. So molecular phases like dense H2 and diffuse H2. Okay. Yes. What is the fraction of the volume occupied by this particular phase? So the denser the phase is, the smaller the volume they occupy, normally speaking. It should add up to 1. If you add up all of them, it should roughly add up to 1. So this is 0.5, 0.1, 0.4. It almost becomes 1 right there. Okay. Volume filling fraction is like what fraction of volume is occupied by this phase. You can also define mass filling fraction. What fraction of mass is in a particular phase? So the volume is dominated by the hottest phase. Mass is dominated by the cooler phases. Okay. And then in addition to these, you also have stellar outflows, which are also quite dense and so on. So, these are some of the things in the ISM. This is actually a table of protosolar abundances of elements with atomic number less than 32. So all the elements, their abundances, protosolar means, at the time of the formation of the solar system. The sun is burning hydrogen to helium in the core, but that helium does not come out at the surface, right? It's radiative zone inside. All that is essentially there. So the photosphere of the sun is assumed to have the same elemental abundance ratio as the primordial sun, the solar nebula out of which sun and the planets condensed. Okay, so by measuring the spectrum of the sun, you can actually model the abundances of these various elements. And this is the power of spectroscopy. Some of these elements like beryllium, boron are so rare, yet the spectra quality is so good and the data is so good, you can find out their abundances. There are two kinds of abundances mentioned here. There are photospheric for a lot of them, and then there are meteoritic. So the meteoritic abundances are more accurate. They are based on certain kinds of meteorites that fall uh, on the surface of the Earth, right? There are meteorites which are sort of always hitting and falling through the Earth's atmosphere. Some of them are supposed to be pristine, right? That those objects uh, have been going around the solar system since the beginning, since the formation of the solar system, and by chance they come, and we can collect their samples. Now, once you have material in your hand, you can do like very, very, very uh, detailed analysis, right? You can actually do mass spectra, mass spectroscopy of those and find abundances in like parts per billion, that sort of a precision. And so these meteoritic, where it says, are measured using meteorites. But this our Earth Sciences department here has mass spectroscopy and so on. They do it even for our terrestrial Earth, terrestrial samples, what fraction, what's the composition, and so on. But these are extremely sensitive. For doing this, you need very high precision and very high ability to even count very small amount. So these are the kind of abundances. So this nx by nh is the number abundance of x relative to the to hydrogen. So you see one, so this is 9.55 times 10 to the minus 2, and there is an error bar there. So about by numbers, you have helium is about 0.1 times number of hydrogen, and so on. So let's see something which is particularly low abundance. So look at beryllium. For every hydrogen atom, you have 2.19 times 10 to the minus 11 beryllium atoms. So, and this is meteoritic abundance. So as I mentioned, the meteoritic abundances are more accurate if you can get them. But meteorites generally do not have gases, right? The gases have all gone. So it's only the remaining non-volatile materials that are in the meteorite. So there is a lot. This is a field in itself, but it's very, very important. This abundances. Matter in the ISM. There is also radiation in the ISM. There is also magnetic field in the ISM. So these are the different things. So the CMB is at 2.7 Kelvin. You can calculate the energy density in the CMB, right? It's AT to the 4. Right? A is the radiation constant and T is the temperature. And this is about this energy density. There is also far infrared radiation pervading the ISM. It has an energy density of this much, right? I had shown you this basically I had shown you this radiation background. It goes from radio all the way to gamma rays, and you can actually calculate how much energy density there is in different bands. So these are roughly the numbers. And the interesting thing is they are more or less within a factor of 10 of each other, all of them. So there is radiation, there is starlight, thermal kinetic energy, 3/2 nkt. Average value is this much in EV per centimeter cube. Turbulent kinetic energy, magnetic energy, cosmic ray energy. Again, these have to be taken with a big grain of salt, but these are indicative numbers. For some of these things, there is a physical reason that why they should be comparable. For example, kinetic energy and turbulent kinetic energy and magnetic energy. Turbulence is supposed to amplify magnetic fields and vice versa. So they are. So if you increase kinetic energy too much, you also build up magnetic energy because of flux freezing and magnetic induction equation. So there are reasons for some things to be close to equipartition, but there is no reason why the CMB should have the same energy density as the other thing. The CMB originates from a totally different mechanism, but that's sort of a coincidence. Okay. So these are some of, this is flow of energy in the Milky Way, right? So there are stars which are held together by gravity and produce energy due to nuclear burning in their cores. It produces radiation. Radiation carries most of the energy of stars. There is a little bit of energy coming out in kinetic energy of stellar winds and supernovae, but it's a subdominant component. This energy is couples to the ISM. It drives the kinetic, thermal, chemical energy, magnetic, everything is driven by stellar radiation, essentially. And then there is also extragalactic photons, general radiation field, which ionizes the IgM, also pervades the ISM, which is this. But most of the radiation inside the disk of the ISM is due to stars. And the ISM in the Milky Way cools and loses photons to the rest of the universe, which goes here. So this is the balance of energy. Most of it is produced by stars in form of radiation. It excites the atoms and molecules, and they radiate away. Radiation which just goes out. So this thick arrow roughly balances this thick arrow. So here is an example of two regions in the ISM with radiation field. So this is radiation field in a neutral H1 cloud. Right. So this is radio. This is UV, and beyond UV, everything is absorbed. So the optical. So once you have hydrogen ionizing photons, they can only penetrate a hydrogen column of about 10 to the 17 per centimeter square. Basically, very little neutral hydrogen is enough to absorb UV radiation, because it's very easy to excite hydrogen once you have enough energy from ground state to free state. Okay, so that's why this is cut off. But let's see what are the different things here. There is synchrotron emission here. There is the CMB peak. This is dust emission in millimeter. These are some lines in dust and ISM molecules. This is just starlight, just stellar radiation. These squares are measurements. Now this is in a normal neutral hydrogen region. Well, now if you look at an H2 region, H2 regions are really these intensely ionized regions close to massive stars. You see the stellar radiation and the dust radiation becomes humongously dominant compared to this. Right? Because you're like exposed right to radiation from a massive star. So this portion, the dust emission essentially increases, and also the starlight component increases. So dust re-radiates the radiation from the star. All right, so this is how you model, right? You have a composite SED, and then you say this is coming from magnetic field, this is coming from CMB, this is free, bound free, blah, blah. But anyway, this is just to give you an idea of there can be very great diversity of radiation fields in different regions of the ISM. Done here. Collisional processes in the ISM. How do we deal with collision? So collision rate coefficient. So when we are, it's sort of very similar to chemical kinetics. You have forward reaction, backward reaction, that kind of those kind of ideas we'll encounter soon. So suppose you have collision between two types of particles A plus B, and it produces some products. Right, so this is a collision between A and B, and it produces something. A and B can be like an electron and a proton, and the product can be hydrogen atom. So reaction rate per unit volume is equal to number density of A times number density of B. Right, these are the species. Number density of A times number density of B times sigma, which is a function of relative velocity between these particles, times V. Right. So for a two-body process, this is the reaction rate density. Right. You have the number density of the two species times the two-body collisional rate coefficient. This thing in square brackets. The square brackets denote sum over all velocities. And here velocities are relative velocities between A and B. So this is called two-body collisional rate coefficient. Okay. So sigma V AB, this is sigma V AB, this is equal to, this is the definition of this is just sigma as a function of V times V F V dV, right? So as I said, this angular brackets denote the integration over all the velocities. So, and this FV is the distribution function in velocity space, or you can actually, do this. You can just put a subscript small v, just to make sure that this is a velocity space distribution function. So we know that FV, for a Maxwell-Boltzmann distribution, we know that FV dV is equal to 4 pi mu by twice kBt, 2 pi kBt, 2 pi kBt, 3 by 2 times e to the minus mu v squared by twice kBt v squared dv, right? This is just the standard Maxwell-Boltzmann distribution of velocities. Here, mu is the reduced mass, right? If you have a collision between two partners which have different masses, then you can actually decouple this problem into the problem of motion of the center of mass plus motion relative to the center of mass, and the effective mass that arises in this problem is this reduced mass. Okay, and the velocity v here is the relative velocity between the collision particles. So mu is equal to ma mb by ma plus mb. These are particles, particle masses for A and B. Ma and mb are the masses of these particles here. Okay. Right, so you can actually see that if you integrate this FV dV, you should get 1. This is normalized so that you get 1. So sometimes it's also useful to consider the energy space distribution function, right? You can consider it in E space or in V space. They are very related because E and V are not independent. It's just a change of variable, right? FE E dE, right, is the fraction of particles with energy within the energy range E to E plus dE. This is actually equal to FV dV, right? So this is how FV and FE are related, and we know that E is equal to half m, no, not m, mu, because we are doing it in this reduced mass, half mu v squared. So you can just do this change of variables easily, right? So we are after this actually. If you look at it, we want to know v times fv. Okay, and if we express or this can actually also be written in the energy space as, so this is a cross section for a given velocity v. You can also have cross section for an energy e. Again, these are related one-to-one mapping. So sigma e v times fe e times dE, right? Again, this is the same. This is another way of writing the same thing, except in terms of energy. So you see, V times Fe arises here because we are doing sigma times V, average over all energies or average over all velocities. They're equivalent. So if we do this change of variable properly, and if you just write V times FEE, and if we use this equation and this form, what you'll get is, let me just write down the final answer, 8 by pi mu kBt, 1/2 times E by kBt, e to the minus E by kBt. By the way, this is based on chapter 2 of this book, so you can actually read it up if something is not clear. So this is what you will do. This is what you will put in there, and then you'll get sigma VAB. So we have the expression for two-body rate coefficient, which is nothing but sigma V AB is equal to, if we plug this expression in that integral, we'll get 8 by pi mu kBt to the 1/2 integral sigma AB E by kBt. This is just this one times e to the minus E by kBt dE by kBt. Right, so it's an easy integral, and energy goes from 0 to infinity. So you'll integrate over energy, right, and right. So this is the general expression for the two-body rate coefficient. Now this is where all the physics is, right? What's the cross section? Once you get the cross section as a function of energy or as a function of relative velocity, you can just get the rate coefficient, two-body rate coefficient. So we'll actually mark this. Okay. Now you can also have three-body processes. In general, generally three-body interactions are rare, but if you have very dense medium or if you have very special conditions, these can also be important. Okay, in that case, what you have is the reaction is something like this. You have A plus B plus C going into products. Three, three is equal to KABC. You know, this uh, three body reaction rate coefficient, this KABC times NA times NB times NC. This is very similar to chemical kinetics. If you've done chemical kinetics, these are the kind of things that you do there. And you can actually think of these processes like collisions and ionization, recombination as sort of chemical reactions. They are, for these purposes, like chemical reactions. Okay. So just a sec, let me go back. Let me get the units right. So this is rate per unit volume, right? This is density squared. So this is centimeter to the minus 6. This is centimeter minus cube per second, right? These many reactions per second per unit volume. So this is centimeter per second. So this whole thing should have a dimension of centimeter cube per second. Okay. So you have to be very careful about these dimensions here, because the sigma depends on what sort of process this is. Okay. For example, in this case, this is again per centimeter cube per second. This is centimeter to the minus 9. So this should have centimeter to the 6 per second, right? So these are, you have to be careful about dimensions. Centimeter cube, centimeter 6 per second. Okay. So even in ISM, three body processes can be important in some cases. For example, in the early universe, when there was no dust, molecular hydrogen, sort of formation of molecular hydrogen involved bringing electron and proton and a neutral hydrogen close together. So there are other situations as well. For example, processes in which you are populating higher ends of, say, neutral hydrogen atom, right? N equal to 100. Normally, we don't think about N equal to 100 level. We mostly talk about N equal to 1, 2, 3. But you can have, in observations, you can have transitions like N equal to 101 to 100. These kind of transitions actually happen in radio, because the energy gap is very small. So some of these things actually may involve three body reactions. So chemistry is really, really complex. Okay. Okay, so now, so this is the general expression for any two-body collisional two-body process. We can actually consider various interactions. So what are those? So we can actually have, say, electron ion. These are Coulomb interactions where potential goes like 1 over r. Now you can have things like ion-neutral collisions. In case of ion-neutral, what happens is an ion will polarize the neutral atom, right? It will induce dipoles, and there will be attraction of that dipole to the ion because of this polarization. So these are ion-neutral collisions, and there the potential the potential energy goes like 1 over r to the 4, where r is the distance between this ion and neutral. Then you can have electron neutral. So you can have a neutral atom, an electron hitting the neutral atom. It can excite vibrational modes or rotational modes in a molecule. And you can actually have so these are the kind of things that we'll consider neutral. like van der Waals interactions. In this case, you can actually consider them as billiard ball collisions, right? If they touch each other physically, you have a collision, otherwise they just move. So these are the kind of things that we'll be considering. Okay, let's look at the first case. So inverse square law. So okay, so you have so there is a charge of charge Z1e, and there is a there is Z2e charge, and we'll actually consider. So this is Rutherford scattering, essentially Coulomb scattering, Rutherford scattering. Right? If you remember this gold foil experiment of Rutherford, that most alpha particles just went through the gold foil, whereas a few were reflected really, really strongly. So that's basically characterizing the cross section of interaction between helium nucleus and gold nucleus. So sort of charge interaction. So that's why this, the rigorous treatment of this is Rutherford scattering. But what we'll do is we'll actually be in this impact approximation, right? If you recall, we did this. We have done this approximation even before. We assume, and we'll actually show that most dominant collisions for 1 by r potential are long-range collisions, not the very head-on collisions do not dominate in deflecting particles. They are very rare. It's the large impact parameter collisions which dominate the overall cross section. Okay. So this is the impact approximation, that even after the collision, so this is the target, and this is the projectile. You can actually think, these are like the standard terms used in this field. So in an impact approximation, you assume that the projectile is essentially unperturbed from its straight line path. But you do have this target gains, is pushed in the perpendicular direction. It gains delta p perp because of this interaction. Okay, we have seen this in the gravitational problem as well. Okay, so let's do it. So if this angle is theta, and this is your charge Z2e here at this point, the force actually is along the line joining the two particles, and this angle is also theta. Okay, so what is F perp? F perp is equal to Z1, Z2 divided by B by cos theta. Right, so B is this impact parameter, B by cos theta squared times cos theta. This is the force at a given angle theta. So that's equal to Z1, Z2 by B squared cos cube theta. Okay, so and dt is equal to dB tan theta 1 by V1, right? So V1 times dt is just this distance, infinitesimal distance moved here. That distance, this distance is just B times tan theta. So you're just sort of differentiating that. This is what we get. This is nothing but B by cos squared theta V1. So what is your delta P perp? The momentum kick in the perpendicular direction in this impact approximation is nothing but F perp. Hmm? Yes, yes, sorry. No. This is d theta. B is constant. Theta is changing. Yes. So there is a mapping between time and theta. You can think of t equal to 0 is the closest approach, and then, yeah, good. So this is nothing but z1, z2 by b squared cos cube theta, and dt is b d theta by cos squared theta d times b1. This now you are integrate. Now this is just a simple integral. So theta goes from minus pi by 2 to pi by 2. Right? This is a simple integral. You can do it. This comes out 2z1 z2 e squared by b b1. So the kick, the momentum kick in the perpendicular direction is proportional to 1 by v1. F, right? So this property of these Coulomb interaction is that if you have a faster moving projectile, it does not deflect as much. If you have a slower moving projectile, it deflects much more, is reflected here, 1 by v1. Okay. So let's actually apply this idea to collisional excitation, collisional ionization, not excitation. So collisional excitation means you have an electron in, say, ground state or lower state, and you have collision, and the electron gets excited to a higher bound state. Collisional ionization is that you have an electron which is bound, you have a collision, and the electron gets unbound. Okay. I be the ionization potential of the bound electron. So so the picture is that if so, you consider the target as the neutral and the projectile as say an electron which is hitting this ion. Okay, so because of this kick in the perpendicular direction, this system will gain some energy. Okay, if that energy is higher than the ionization potential of this ion, then the electron can get kicked out. Okay, so if your velocity of the electron is greater than twice I by me, right, then the ion can get further ionized. So delta P perp should be greater than twice me times I for ionization. So delta P perp squared. Oops, sorry. Right, so P squared by 2m is the energy that this electron sort of gains from this kick. So all the collisions for which your P perp is large, you can get ionization. And if you look at delta P perp expression, is here. A larger delta P perp means smaller b. The particles which are coming closer can ionize because they exchange higher energy. If you have an electron which is moving like at a larger distance, it does not give this ion enough energy for it to get ionized. Okay, so B has to be less than B max. which is a function of V for ionization. And Bmax is equal to square root of 2 square root of MEI times ZP E squared by V. Let's see. So what am I doing here? Right, so this is delta P perp. So delta P perp, critical is equal to twice ME times I square root of that. And that is nothing but this guy, twice Z1, Z2, E squared by B max V1, right? So this is equal to this. So this B, this B max correspond to this ionization potential. So you can actually calculate B max from there. And if we are considering electron-ion collision, then one of the Z's is 1, right? It's an electron. And the other thing is like the proton or whatever, Z of the ion. So basically you only have to consider cross section for B's which are smaller than this B max. Okay. So the sigma B is roughly equal to pi times B max squared. So only these B's which are less than this B max will be ionizing this ion. So this is actually equal to 2 pi Zp squared e to the 4 by MEI B squared. This is the collisional cross section. So what is sigma V? The rate coefficient, the collisional rate coefficient, is equal to this sigma V times V times FV dV, just the definition. And so you have to plug this into this guy, right? And your velocities, this is a velocity integral, so it will be V min to infinity. Only the projectiles which have velocity greater than a certain value will be able to ionize this ion. And that V min is nothing but twice I by ME. So I is the ionization potential. This is just half ME V min squared is equal to basically the energy of the electron has to be at least equal to the ionization potential for it to be ionized. Okay. So what do we have? We have 2 pi Zp squared. I mean, this is in the book. Just try to focus on what I'm saying. No need to write it down. MEI. And then we have the integral 1 by V squared V times 4 pi ME by 2 pi KBT 3 by 2 V squared e to the minus ME V squared by twice KBT dV. And this goes from V min to infinity. Right. So the way to do these integrals is do a change of variable from V to a dimensionless quantity, bring the dimension full things on the left, and then the remaining integral will be just something out of unity. Okay, if you do all that, what you get is Zp squared 8 pi ME KBT to the 1/2 e to the 4 by I e to the minus I by kBt. This is the collisional rate coefficient. So let's see, what does it mean? So if you have if your temperature is small, if your temperature is low, your rate coefficient is actually high, except except when this, you need enough temperature. At high temperatures, of course, the exponential will kill you. At low temperatures, the exponential will kill you. You need particles to have energies of order at least I. If your I is much bigger than kBt, you will not be able to ionize it. But if your I is much less than kBt, your cross section is, or the rate is, so if your temperature is low, then rate is high because of 1 by square root of T. And there's also 1 over I dependence. So so let's actually consider, say, hydrogen. For hydrogen, ionization potential is equal to ionization potential of hydrogen in the ground state divided by n squared, right? Where n is the level, not the number density. N equal to 1, equal to 2, and so on. And IH, of course, is 13.6 eV. So if for large n, say, 100, so n equal to 100 level of hydrogen, almost unbound electron. In that case, and if your plasma temperature is about 10 to the 4 Kelvin, this is the warm interstellar medium temperatures, or warm neutral medium is 5000 Kelvin, about that. In that case, kBt is much greater than I, right? Because this is 13.6, so this is about 1 eV. Now it's 1 by n squared, so it's 10 to the minus 4 times 13.6 eV, which is smaller. So your I is much less than kBt. So in that case, this exponential becomes 1, and your sigma v is inversely proportional to t to the 1/2. And if we plug in I, so this is 1 by IH times n squared, right? So what it means is that for high n, so for an electron in a high n state, the cross section for ionization is very high. It in fact goes like n squared. So if you have a collision with an electron of an atom which is in a highly excited state, it will very easily get fully ionized. Okay, because ionization potential is low and the geometrical cross section is high. So this is one example. There are other concepts. So there is deflection. So there are some time scales related to collisions. Okay, one is deflection time. So what is meant by deflection? So imagine you have a proton and you have an electron, and electron gets sort of scattered a little bit, but we are actually, as I mentioned, these Coulombic interactions are dominated by large B's, and hence are small angle scattering. So if one collisions will not deflect it. You will need many collisions in order for it to forget its initial direction. Okay, so what is the deflection time? So we have d dt of delta p perp squared is equal to Right. Integral B min. So you remember the Coulomb logarithm? It will appear again because it's the same scattering that we are doing. B min to B max. 2 pi B dB N2 times V1. So this is the differential area from B to B plus dB. N2 times V1 is the flux of uh, target particles as seen by the projectile. So this is, this whole thing is basically rate. Flux times area is a rate. And we have this delta P perp squared. If you look at the expression for delta P perp squared, here it is. We're just going to copy it there. Two times Z1 Z2 E squared by BV1. This was delta P perp and this is squared. The other thing to remember is that there is no preferred direction in the perpendicular direction. Some kicks will give you momentum in the negative direction. Some kicks will give you a random kick in the positive direction. On average, you won't get deflected in either direction, but you will do a random walk in deflections, and eventually your spread in angle becomes order unity. That's when you have a 90-degree, that's the deflection time when that happens. So this is nothing but delta P perp squared. Okay, so if you write this down, this is 8 pi N2 Z1 squared Z2 squared by V1 log B max by B min. Again, this Coulomb logarithm. So there was 1 by B squared and B dB. That gives you that Coulomb logarithm. So what is B min? Someone remembers? The minimum value of B that we put in this is when the deflection is no longer, after deflection, the particle no longer moves in the straight line. That is, yeah, or B90. That's right. So B min is when this impact approximation breaks down, or the kinetic energy becomes comparable to the potential energy. That's when the deflection is substantial. If the kinetic energy is much larger, it just gets undeflected. So B min corresponds to is equal to Z1 Z2 E squared by energy, right? E is the energy, kinetic energy, half mu V squared. And if Z1 Z2 E squared by B min is equal to energy, that's when the deflection is substantial. So that's B min. What about B max? In the gravitational problem, B max was the size of the system, right? If your stellar distribution ended, there is a, you break down the fact that there are more stars on this side than on this side. Whereas in a plasma, there is this shielding of charges. In the gravitational problem, wherever you put matter, it will affect you here. But in a plasma, if you put electrons, or excess charge somewhere, the plasma electrons respond and shield that charge through a process called Debye shielding. Okay, so the B max is, so for this problem, you should not consider any electrons which are beyond a Debye length, because for them there is no excess charge. They are this charge, this target has been shielded for that electron. So B max is equal to the Debye length, and the Debye length is equal to V thermal by omega PE, where omega PE is electron plasma frequency. So this is actually equal to KT over 4 pi NE E squared to the 1/2. Okay, so in an ideal plasma, lambda d is much bigger than B min. So in an ideal plasma, the number of particles within a Debye sphere is very large. That's why shielding can happen. You require a lot of charges in order to compensate the excess charge that you put. So these are the limits of this integral that you have to put. So if we plug in this and this, so you have log lambda is equal to uh, basically, if you plug in the numbers, this is sort of roughly in the range 20 to 35. The nice thing about the log function is that even if you make like orders of magnitude mistake in estimating B max and B min, the error you make in the final expression is small. So, no one really bothers much about calculating it super accurately. First thing is, so this is the deflection time. So let's go back. Right. So this is basically log lambda, Coulomb logarithm. This is the Coulomb logarithm. Right. So this is ddt of delta p perp squared. Okay. So there are two time scales that we should consider. One is the energy exchange time. So say you have an electron and you have an ion, and if you give this electron some velocity and it interacts with these ions, what is the time scale on which they share their energy? This is the energy exchange time scale. So, or energy loss time scale. It's the same one and the same thing. So T loss is the definition of T loss is energy divided by dE dt loss. Right. And what is this? This is half m1 v1 squared. M1 is the mass of this projectile. dE dt loss is what? Okay. Now, so you have d dt of delta p perp squared by twice m2. Notice, so we have actually done this when we did dynamical friction. If you recall that when you had a massive mass capital M moving, these particles took away the perpendicular momentum, but the longitudinal velocity also reduced a little bit in each of these things, but the reduction was much less. Okay, so this so what happens? So you have this particle 1, this is particle 2. Particle 2 was at rest, it gets a kick in this direction. Particle 1 gets an equal momentum kick in the other direction. So delta P1 perp in magnitude equals delta P2 perp, right? But the energy exchange, energy lost by 1 is equal to this. The rate of energy lost by 1 is equal, so no, it's an internal force. So whatever energy that 2 gains, 2 had 0 energy in the horizontal direction. So whatever energy that 2 gained is equal to the total energy lost by 1. So this is that. This is the energy gained by 2, which was at rest. Right? So that's why this is energy loss time scale. So this is equal to m1 m2 v1 cube divided by, so I can just I have this expression for delta p perp squared earlier, right? Here it is, this one. This is delta p perp squared. So if I plug that in, I have m1 m2 v1 squared, and there is a 1 by v1 from here. Eight pi n2 Z1 squared this is N2 Z1 squared Z2 squared e to the 4 log lambda. So this is already integrated over B. So in fact, this is what I wrote down there is this actually. So there was a 1 over V1 there, and that brings in V1 in the numerator. So this is your time. So this is the loss time scale. This is the time scale over which the projectile and the target exchange energy. Now, the other time scale is the deflection time scale. So actually, it's useful to think physically. Suppose you have a proton and an electron. Okay, an electron is sort of shot on the proton. The electron get deflected easily, but it will not like push the proton sufficiently. Like, you know, if you have a massive ball and a small ball, if the small ball hits the massive ball, it gets reflected. It has exchanged momentum with the massive ball, but not energy because it's an elastic reflection. V goes to minus V. So the deflection timescale in this problem of balls with very different masses, the deflection time is just one collision. But the energy exchange time would be many collisions. It would require many collisions between a massive ball and a small ball to exchange energy. Okay, so the same thing actually applies here. So T deflection is equal to M1 V1 the whole squared. So this is parallel momentum squared divided by rate of change of delta P perp squared. Right? You know, when do these random kicks in the perpendicular momentum become of order the RMS velocity in the horizontal direction? Now, P squared by yeah, this is momentum, this is momentum, this gives you a time scale. So here this factor of 1 by M2 is not there. So this is nothing but M1 squared V1 cube by 8 pi N2 Z1 squared Z2 squared e to the 4 log lambda. There's a very important difference between this and this. Here there is M1 M2. Here it's M1 squared. So the two time scales for an electron-proton collision will be a factor of 2000 different, because the ratio of proton mass to the electron mass is 1836. So this is actually an important. So you can isotropize your momentum on a much shorter time scale compared to being able to exchange energy. So this is also called equipartition time. Equipartition. And of course, you know, V1 is like a RMS velocity, you know, 3 kBt over M1. So you can actually write this velocity in terms of the thermal, you know, the temperature. So this is actually very important, that the energy exchange time scale and the deflection time scale can actually be very different. So electron-proton energy exchange by T, you know, deflection is about 1836. So for typically, you know, if we plug in the numbers for these, right? So this is the last topic we'll do. Just let me write down so T deflection is like, you know, 8 times 10 to the 3 seconds TE by 10 to the 4 Kelvin to the power of 3 by 2. So the deflection time becomes longer for higher temperatures. In higher temperatures, particles have faster velocities, and faster velocity particles just zip through. They don't get deflected as much. Centimeter to the -3 by NE. Higher the density is, higher the target density, the faster the deflection will happen. So there's a 1 by N dependence here. And then 25 by log lambda. This is deflection time. What about T equipartition or the energy exchange time? This is 2000 times longer, so it's about 1.4 times 10 to the 7 seconds. The same dependence, right? The other dependencies are the same. But even this time, like 10 to the 7 seconds is like half a year. Half a year is nothing for ISM timescales, right? Mega years or higher, longer timescale. So in a lot of situations, right? For example, number density of order 1 particle per cc, temperature of order 10 to the 4 Kelvin, you can assume the electrons and protons and all the ions to have the same temperature. So anyway, we'll end with this, and we'll continue in the next class on this and related topics.